right. So I guess we gotta keep going through this stuff this way. We'll see what happens. Yeah. So let's get through this. Going through these slides on 5.7 and 5.8, they're all about reaction mechanisms. Really, actually going through these slides, what we covered in 5.4 at the end of those slides is about reaction mechanisms. And honestly, there's nothing new here that wasn't in those slides. So there's a couple more problems and stuff on here. And so we'll just kind of go through those. So you can meet my cat Finnegan here. So, all right, so we'll get through these. But there's nothing new here that was not in 5.4. So let's go through this, okay? We even saw, I believe, this same problem in 5.4. So it says we're decomposing hydrogen peroxide. It's catalyzed by iodide. Here's the overall reaction. But then we find that the rate law is this, where iodide is in there and it's just times H2O2. Okay, what's the reaction order with respect to each of these? They're each to the first power, so they're each first order with respect to those. Looking at this reaction and the rate law, we know it cannot be a one-step reaction, because if it was, the one step of the reaction would be the elementary step, and you can use the coefficients from the elementary step. Those would be the same as the reaction orders. So if this reaction did happen in one step, the rate law would be rate equals K times peroxide squared, and that would be it. But because the rate law is not that, we know it has to take place in a couple steps. So some scientists come up with this reaction mechanism. This is not the only proposed mechanism for this reaction, but here we go. And we look at this, identify any intermediates or catalysts. Well, we consume I negative at the start. It gets pooped out at the end. That's a catalyst. We make an IO minus. We consume an IO minus. That's an intermediate. All right. And then from that, we can see each of these steps is only bimolecular. Okay. There's no termolecular or trimolecular steps in there, which is a good thing because those are rare and they likely wouldn't happen. And then the step one would be the slow step, the rate limiting step, because if I did the rate law for that, it would be rate equals K times peroxide times I minus to the first power, which is what this slide showed. Not too bad. All right. Now, if you had a problem that gave you this mechanism, and then it gave you a second mechanism that was almost identical, but say it had like 2I minus right there, that mechanism would not be as valid because that would be a termolecular step, which is unlikely to occur. Okay, we now know, we saw these reaction profile diagrams in 5.6. So we can, this says how much the concentration molarity of our intermediates and catalysts we have in our reaction. We know our intermediates are step one. When it creates the products from step one, that's down here, this little trough. So there's our intermediates. And this says the actual amount of IO negative in our beaker is going to be very low because any of it that's made is going to be produced it's going to be consumed in a faster step right after. Okay? Remember, these fast steps happen very fast. So anything we make is just going to be instantly consumed. And so if we're trying to monitor how much of this stuff we're making, it's going to be difficult to monitor. The I negative, it says it's going to be unchanged by the end of reaction because we used it, but then it reproduced it. So it's kind of hard to tell what's going on with that. It kind of disappears for a little while and then it gets reproduced. Now it says, given that the rate law was that K times peroxide times I minus, it says step one is going to have the higher activation energy. Step one is going to be the slow step, the rate determining step, because that step one gave us that as our rate law. To actually confirm if that proposed mechanism is valid or not, we usually have to do some other type of method, usually spectroscopy. Because remember what spectroscopy is doing, it's trying to confirm what's what chemicals and what types of bonds are in there. Because remember, we can actually measure like the vibration of those bonds, so we can tell what bonds we actually have in there. So we can use spectroscopy to detect the presence of certain things like intermediates. Okay? Now, we know that the rate laws are determined by the speed of the slowest step. That's the rate limiting step. And the first step being rate limiting is the easy version of all of this stuff. Okay? In that it's easy because the elementary steps, we can use the coefficients as our reaction orders. Okay? And then remember, if the slow step comes after that, you cross out any intermediates or anything that was produced and then reconsumed. You add up all the reactants left over. We're going to get back to that in 5.9 specifically. Pre-equilibrium approximation, and figure out other ways to deal with the first step not being slow. So here's a different reaction. We have NO plus Cl2 make NoCl2, and then the NoCl2 reacts with another NO to make 2 NoCl. We are told the first step is the slow step, so that's our rate limiting step. It says by examining the collisions of that first step, we know that the rate law for this first step is just going to be rate equals K times NO times Cl2. There's no coefficients, so there's no exponents besides 1 right there. Okay. It says because the first step is the slow step, we can infer that the rate law for the overall reaction is this same rate. Okay, that's what we're saying. That the slow step is the rate law for the overall reaction. Says if the rate law for the overall reaction is known, a mechanism can be supported or rejected based on the rate law of the slow step. This is what I was saying. This is one of the things you have to validate if you have a good mechanism or not. So here's an overall reaction here. 2H2 plus 2NO makes N2 and 2 H2Os. It says if the rate law of the reaction shown above is experimentally determined to be rate equals K times H2 times NO squared, so first order for H2, second order for NO, can the following proposed mechanism be correct? Well, first thing, okay, we know this reaction doesn't happen in one step, because if it did, it should be second order with respect to hydrogen gas also. All right, so we're given these steps here. 3 steps for the reaction. It says slow step is the first one. Okay, first confirmation would be, do these 3 steps add up to the overall? Okay. And so you would cross out any intermediates, so that N would cross out. Here, I can draw on this. So this N is produced and then consumed. This O is produced and then consumed. Okay. Anything else here? No. So what's left? Well, what's left here? We have 1 H2, 2 H2s. That works. 1 NO, 1 NO. So we have 2 NOs. 1 H2O, 1 H2O, 2 H2Os, 1 N2, 1 N2. We're good. So it does. It adds up to all of those. Okay. Now, how do I get rid of all these? Okay. Clear all. Okay. So if we're saying the slow step is the first step, then the rate law of that first step would be rate equals K times H2 times NO. Right? First power, first power. So does this mechanism support this rate law? No. Incorrect. All right? This mechanism also wouldn't support the slow step being in any of the other ones, I believe, either. This whole mechanism is wrong. We'll see that when we get to 5.9, and because we would have to deal with this H2O. Okay. All right. And that's it. That's the whole, both 5.7 and 5.8. So it's the same stuff that we've been doing for reaction mechanism. Let's do this one together. So write the overall reaction represented by the mechanism below. Step 1, step 2. We're not told if it's slow or fast because we're just asked to write the overall mechanism and identify intermediates and catalysts. So we're not asked to find the rate law. Okay, so let's do this. So let's see here. You know, it's really hard for me to write on this, but that's okay. You guys can deal with it. So N2O makes N2 and O. Then the second step, we use this O, so who cares about that? Cancels out. All right. Well, what's left? We have two N2Os, two N2Os. No other reactants, nothing else on the left side, so arrow. We have two N2s, two N2, and an O2, plus O2. Man, writing with math sucks. Okay, so the thing we crossed out there, is that an intermediate or catalyst? That's an intermediate, because it was produced and then consumed. A catalyst would be consumed and then produced. And nothing's doing that, so there's no catalyst in this reaction. All right? Cool. So let's see here. I think we got another problem. So this one, we have another decomposition of hydrogen peroxide here. It says, use the reaction mechanism below to determine the rate law for this reaction. Okay. All right, so we have all that stuff there, right? We could prove that it's the same. Okay, let's do that. Might as well get some practice there. H2O2 plus I makes H2O and IO. We then use that IO, so it cancels out. This I minus gets reproduced there. Everything left, two H2Os, two H2Os, or two H2O2s, two H2Os, and an O2. So we match. We are told that this low step is this first step. So the rate law would just be rate equals K times H2O. The concentration of H2O2. Now, what about this? What about this? We crossed it out because it was a catalyst, right? So it doesn't show up in the overall. But here's the thing. When I'm looking at this single step here, this I has not been canceled out yet. It's still a reactant there. And so it still has to show up in the overall rate law. Okay. So the rate law is going to be rate equals K times molarity of H2O2 times molarity of I minus. Okay. So catalysts can show up in the rate law even though they don't show up in the overall reaction. All right, so we've seen that. And I think that's it. Okay, so that's 5.7, 5.8. Work the other problems you have, and that's about it. I'll make a video on 5.9 and the rest of Unit 5 next week. Dear God, I hope we're back in class, because I don't know what we're going to do after we get through the Unit 5 stuff, because I did not copy over my Unit 6 stuff to my personal account. So we'll deal with that bridge if we have to. Okay, get involved. Okay, the more people we can get involved, hopefully the faster this thing can be resolved. Okay, I'd love to see you guys out there with us. So, all right. Well, have a good weekend. I'll see you guys soon.